Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome back. We are in the second set of lectures. We are discussing biosensors, different types of biosensors, and corresponding sensitivity. Now, today we'll be discussing the second set of nanobiosensors, which are amperometric. Now, you may recall that there are these three types of biosensors we promised that we'll discuss. One is this potentiometric biosensors, where the biosensors is like a camera for the charge. And so therefore, when the yellow molecule lands on the sensor, which is often a MOSFET in this particular case, it changes the potential of the channel, and that changes the corresponding current. Now, of course, that would be really very good because it can be miniaturized, integrated with other components. So that's a very good thing, except that we saw that this salt was the troublemaker. Salt was necessary so that the molecules can stay together. Like the DNA, they are both negative. And therefore, in that case, unless the salt was present, they will simply fly apart. And same was the case for protein and antibody binding. Without the salt present around it, it would be difficult to manage the interaction. So in that case, of course, the trouble was that a significant fraction of this yellow charge was sort of being taken away as tax for helping the molecules sort of by the salt itself, and a very little amount was left, and that gave rise to this logarithmic dependence. So this is sort of a screening problem of potentiometric sensors that we saw there is a way to get around, like using high frequency, but in general this continues to be a concern. The second sensor that we'll be talking about today, and the third one, the cantilever-based sensors, neither have this screening limit as sort of being as detrimental as the potentiometric case. So let's get started with the amperometric sensors. And the basic idea is that in amperometric sensors, we'll see that it is the electron affinity of the yellow molecules and its ability to catalyze or change the property of the electrode itself that will give rise to a current. And so when the molecule arrives on the sensor surface, this current will tell us, the current flowing through this circuit will tell us that a molecule has landed, and that will allow us the detection. That's the sensing. So let's see how it works. Now, before I get there, I just want to remind you through the historic context that these amperometric sensors are very important. I told you about the potentiometric sensors and how eventually towards the end of this course, we'll be talking about how potentiometric sensors are used in genome sequencing. But one of the most important sensors that you will see most people routinely use, like my mother has diabetes and she uses this type of glucose sensors all the time. So when you're talking about amperometric sensors, we are essentially talking about sensors such as the glucose sensors. So it's very important in terms of the biosensors that we routinely use. Now, if you really took a closer look at a glucose sensor, then you would find the following, that this has multiple layers, this strip. It has multiple layers, and the most important layers are the electrodes. So one would be the counter or the reference electrode. One would be the working electrode. So when the blood comes in, it will first react with some enzyme coating. Then there something will happen that will be picked up, that reaction products will be picked up by working electrode, and a current will flow between the working electrode and the counter electrode. And so therefore, what we will see that the glucose content in the blood will be reflected as a current flow. Now, I would like to break it down and explain each one of these steps very clearly so that eventually when you talk about DNA sensing using a very similar amperometric sensors, then things are crystal clear to you. Now, the way to view a glucose sensors, I find it most convenient if I divide it into two parts. One part is the normal sensor. So I have two electrodes. Platinum would be the working electrode, and AgAgCl, silver chloride electrode, will be the counter electrode or the auxiliary electrode. And we will see that we have to apply a voltage. I'll explain why in a little bit. And what will happen, that this is sort of the key sensors. So it will sense the main analytes that we are interested in. And the second part of this sensor, which are actually together, but I have, for conceptual reason, I have just pushed it apart. So we'll see that the glucose coming in from the blood, the glucose coming in, and it reacts with oxygen. A gluconic acid will get out, and a hydrogen peroxide will be produced as a reaction product. Now, this can only occur in the presence of an enzyme called glucose oxidase. And the enzyme allows the specificity. That is, only when the glucose comes is it catalyzed by this oxidase so that this reaction byproduct forms. Now, this sensor cannot detect glucose directly. You know, that's what we are after, sensing glucose. But instead, what it does is that when the hydrogen peroxide comes in here, once gated by this enzyme itself, then it will react on the surface, on the platinum surface. 2 electrons will get out and 2 protons will get out. I'll explain all of them, why such an electron comes out and why the protons come out. But for the time being, just the outline of the problem. 2 electrons will come out and the 2 protons will go through the fluid. This is the 2 electrodes separated by a fluid. And the protons will essentially recombine with the electrons that came from the other side. And in the process, there will be a current flow, which will be proportional to the amount of hydrogen peroxide, which in turn will be proportional to the amount of glucose present. So simply by looking at the current flow through this sensor, I'll be able to say how much glucose has been around. Whether the glucose blood sugar is too much or too little, I'll be able to find out by simply looking at the current. So that is the essence of an amperometric sensor. The physics will come in a second. It is very important to realize that this enzyme allows the specificity, that only when glucose comes can the reaction occur. And so therefore, this hydrogen peroxide, the platinum itself, doesn't have any specificity with respect to this. Only when hydrogen peroxide comes, assisted by this catalysis process, will a current flow. So I want to explain to you how the sensor works, and so we'll go one step at a time. Now, the reaction that happens on the right-hand block, remember where we had glucose and oxygen and the reaction byproducts, that's the top equation. You see the glucose molecule reacting with oxygen. This is the enzyme, and the reaction byproducts are hydrogen peroxide. And then there are this hydrogen peroxide goes to the platinum working electrode. 2 protons are generated, 2 electrons are generated, which flows through the wire, remember? And the 2 proton goes through the fluid, and therefore a circuit is completed. So I will start by this second set first. I'll start with this second set first, and then in the next lecture we'll go back and look at this. And then we'll put everything together in order to see how amperometric sensors can be used for DNA sequencing. So let's get started. So before I do so, let me just briefly highlight the important points. The important points are that the reason why we are using amperometric sensors, that it obviates the problem of screening. The salt screening associated with it will no longer be as important. Remember, these are electron hole flow. And electron holes, these things are all charged. So eventually the effect of potential will still be there. Close to the electrode will still be there. It is just that it will not be as sensitive to screening as the potentiometric sensor was. Because in this case, we are working on electron affinity, as I'll explain, not the potential itself. Now, this specificity comes from this oxidase, because that allowed specific molecular recognition. You see, just like the DNA binding allowed us specificity or a specific antibody, when the protein molecule came around and exactly sort of matched with this, that also gives specificity. So in this case, the enzyme gives the specificity for the reaction. So a random product will not simply be recognized. And as I said, a broad range of sensors are actually used. Now, the important point is that these sensors have a different type of sensitivity for sure. But still, the molecule have to first come in. Remember about the example of the bird. I said that the birds, unless it comes to your focus of your camera, then it doesn't matter how many megapixels of camera you have. So the diffusion limit is still there. And the other thing you saw that there are multiple electrodes. Here already 3 electrodes, which are often difficult to miniaturize. And that is a concern. And so therefore, putting all these things together and is still a big technological challenge. That's why the glucose sensors that you see in the market are so amazing. Think about the millions of people who are using it, who know nothing about biochemistry, to sort of control their food intake every day. And unless this is quite reliable, this would be a very difficult problem. So it's remarkable advance in technology has already occurred despite these problems that are associated with it. So let me explain now the physics of, or the chemistry of how things go. Now, we will begin with the left side, and we'll begin with this basic sensor, and the next lecture will come and discuss the component on the right. Let's go back to college. That would be many years from now for me now, but I still remember this experiment in college where you put copper sulfate, that's the solution, the greenish solution, and if you put zinc in it, a sort of a small electrode of zinc or a small piece of zinc in it, then what happens, you will see that gradually this copper sulfate becomes zinc sulfate, pinkish, slightly pinkish color, and zinc begins to dissolve, and there's heat produced to it. Now the question is, why does it occur? Why does it occur? And the reason it occurs is because we have zinc, when it relates to copper, when it reacts with the copper, then zinc becomes positively charged, goes in the solution, and copper accepts the 2 electrons from the zinc, and as a result, zinc with copper becomes neutralized. And so therefore, we have zinc sulfate and copper. Now this is good. You could say that this reaction is a spontaneous reaction, and this is often you are given the analogy is as if you're going downstream, just like water falls under the force of gravity from the top energy to the bottom. The zinc goes to copper. The electrons go from zinc to copper in an analogous manner. Now, it is relatively easy to see why that happens. If you recall the oxidation potential. Oxidation potential is essentially just desire to give away the electron. If you think about the oxidation potential for zinc, it's quite high. It doesn't like its electron, it just wants to give it away. On the other hand, copper is very happy to accept electrons. Its oxidation potential is negative, minus 0.337. So what happens is that when you put them 2 things together, electrons will go from zinc to copper, and the reaction will proceed spontaneously, and this excess energy will be liberated as heat, something that you can see. Now let's say you don't want this to be wasted as heat, but you want to also go inside and look at how with this current flow process itself. How would you do that? Turns out that it's not too difficult. What needs to be done is that this reaction which is happening on the same chamber you split it into two. So we have zinc on side and copper electrode on the other side, and you hook it up with a wire. And here is your ammeter. You can measure the current. And so now what will happen, that if you put zinc in zinc sulfate, let's say a solution, zinc is very happy to go back and forth. It can ionize and deionize, going back and forth. But let's say it goes from zinc to zinc sulfate, zinc positive ions. And the corresponding electrons that have been left behind will now flow to copper. Remember, copper is happy to accept electrons. And these electrons will then be, this copper is in the copper sulfate solution, the electrons will essentially neutralize the copper ions. Now that's very good, but that's not the end of the story, because as soon as the copper has been neutralized and deposited on this electrode, this nitrate will essentially be alone because its partner has been neutralized. This will go and react with sodium, which is part of a salt bridge, allowing only passage of ions, no electrons, just ions. So nitrate will work with sodium, removing the sodium in the process, liberating an NO3. The NO3 will go and talk to the zinc. They recombine and zinc nitrate is formed, and everything has been back to normal. The extra zinc that came in the solution now has been reduced to zinc nitrite, which has become a part of the solution itself. So gradually these two processes will continue. And so therefore, you will see that between zinc and zinc plus, there's an easy transfer between the electrode and the solution going back and forth. And then there is also an easy transfer between copper and copper plus. And at the end of the day, and once these two reactions are complete, then the process can continue. So in this case, instead of the heat, what we have is the electrode itself. The current can be directly measured, and you can get it by joule heating, corresponding joule heating. Okay, that's very good. When the electrons wants to go somewhere from the high energy level to the low energy level, and there is no barrier. That's not a problem, because now this process can occur spontaneously. However, think about putting zinc in water. Now in this case, going back and forth, unlike zinc sulfate, would be very difficult. And so therefore, the electron which is sitting in one of the electrode now have to go up first before it can go to the other electrode. And if this level is sufficiently high, then there's nothing is going to happen, because these electrons will find it inconvenient. Although there is a net desire to go from this point to this point, but net driving force, but the electron itself will not be able to initiate the reaction in its own chamber, and therefore no current will flow. It's like putting an insulator between two metals. Two electron may want to go from one metal to the other, but the insulator is sort of preventing it. Now assume that you have just introduced in the solution a material or a set of molecules which has a slightly lower oxidation potential. Now it is still difficult for the electrons to go here and then to come back, but at least it is easier than going to the top level, energy level in the original solution, let's say zinc in water or platinum in water, and then to come back. Now, this new molecule, of course, once it comes in, will facilitate the process, and there will be a little bit of current flow, because the electrons will be able to go, and then it will be able to go to the other electrode. However, this current will be exponentially increased if we do the following. That instead of this level, we apply a positive bias so that the level moves up. Now, of course, it's much easier for the molecule or for the electrons to hop back and forth. And as a result, this process of there'll be oxidation and reduction of this molecule. By the way, the word oxidation in this particular, the reduction means simply accepting electrons, and oxidation means giving away electrons. So this process of giving away electrons and accepting electrons would be the reduction, oxidation and reduction process going back and forth. And as a result, quite a bit of current will flow, although the original solution had no current flow. So this is a way one can then recognize a molecule through this forced oxidation reduction, where you have applied a small amount of voltage to facilitate that process. And we'll be using it quite a bit, as you will see. So now let's look at this solution, this particular configuration. We have platinum electrode. Remember, I'm going to go back to the amperometric sensor, the glucose sensor. So we have the platinum on one end, and we have silver chloride on the other end, you may remember. And when you have the system on its own, no current flows, because the platinum cannot come here like zinc did, because in this water, there is essentially no way to initiate the reaction. Although you have put a small amount of voltage, no current is flowing, essentially, very small, let's say. Now what you can do is bring in this hydrogen peroxide. Hydrogen peroxide will have lower oxidation potential, and so as soon as you put 350 millivolts, this reaction will begin. And what will happen that the proton will come this way, and the electron will go, and this process will continue. So although it's not a spontaneous process, however, with this voltage, with this applied voltage, it becomes much easier for this reaction to proceed. And so therefore this current becomes directly proportional to the hydrogen peroxide concentration, which is also directly proportional to the glucose concentration. So this is how the sensor would work. Once again, I show you the same picture, that this is the platinum level, let's say. It's not exact level, it's a cartoon. This is my hydrogen peroxide level. This reaction is initiated when I have pushed it up by 350 millivolts, as say, and therefore the whole process can continue. Now very quickly, let me tell you a little bit about, so we have been talking about two electrodes, platinum and silver chloride, no problem. But let me very quickly tell you that why often two electrodes are not enough. Remember, in the case of a glucose sensor, we had 3 electrodes. There is very important to have a reference electrode. Why is this? Because even when you have platinum silver and you can measure a voltage or measure a current, the problem is that if you wish to control this voltage, remember we want to do it 350, add the platinum electrode so that the reaction can occur. If you simply apply a voltage of 350 directly between the 2 electrodes, then it may not really work. The reason is that when you put, let's say, in this particular case, say I apply 0.8 volts rather than 350 millivolt, then I cannot a priori say what fraction will get onto the working electrode and what fraction will get to the other electrode, let's say the counter electrode. I cannot control the partition of the voltages. And if I cannot control it, then of course I may not have a controlled reaction. For every voltage, there'll be slightly different reactions. So I have to do something about it. And the way to do it is to insert a sort of a third electrode, so that which maintains its potential at a given reference value. And then with respect to it, then you move things back and forth. And so the working electrode then will always have a fixed potential with respect to the reference electrode, and the reactions will be controlled reactions rather than arbitrary reactions depending on the exact configuration of the sensor itself. So therefore, often you will have a 3-cell. There will be a fixed difference between the reference electrode and the working electrode, and the reference electrode and the counter electrode, so that you can rely on the reaction that is happening between the working electrode and the analyte that you wish to detect. So let me then very quickly show how this whole process works. So we are thinking about hydrogen peroxide coming in and giving away its electron, which is getting oxidized in the process. and this reduced species is getting oxidized, and of course, and leaving the electron, here. Remember, when the electron goes out, the current flows in the opposite direction. But of course, there are lots of electrons here, so that reverse reaction is also possible. That HO2, which has just been liberated, the proton which is hanging around, and the electrons, together, they can also make H2O2, also hydrogen peroxide. So both forward reaction and reverse reaction, both are possible for oxidation and reduction. Of course, depends on the exact voltage that you have applied. And so in this case, the net current that flows is proportional to the forward reaction, giving electrons, and the reverse reaction, taking electron back. And so giving and taking it back, the difference of it multiplied by the area of the electrode gives you the current. And of course, it depends on the voltage also. The voltage is, let's say 350 millivolts here, determine the KF and forward and the backward reaction rates. And so specifically, in this case, we'll have a hydrogen peroxide and an oxygen. These two are R and O in our case, and that will determine the current, provided the 350 millivolts dictates KF and KB. Now, this equation is extremely important. This is called a Butler-Volmar equation. Anytime you have an electrode where a electrocatalytic process is going on, something is getting reduced and something is getting oxidized, the forward and the reverse reaction is always given by this very simple formula. Of course, there are more complicated versions of it, but for this course, the only thing we need to remember that if the forward reaction is sort of strong by applying a voltage, for example, so in that case, what will happen, this you can almost neglect with respect to this, and then you can see the current will become proportional to the hydrogen peroxide concentration, and which will then indicate how many glucose one has in the blood. And so here is an example for specific examples. So for example, here you have a set of carbon nanotube. Let's not worry about exactly how they were fabricated. Here is a electrode. You see this palladium electrode, and correspondingly there are the sensing regions, small sensing regions, which looks like a nanocube. So this is really the working electrode that we are looking into. And if you go ahead and then start bringing different amount of hydrogen peroxide into the solution, then what we'll see that the current would essentially jump in steps, because every time you have a different concentration, remember the current in the amperometric electrode is directly proportional to the hydrogen peroxide, and so therefore for every concentration there will be a response of current. It will stay flat for a little bit approximately. Then if you increase the response, it will go up, there will be more current, and so this is almost linearly proportional to the amount of analyte. So just simply by looking at how much current you have in the sensor, you could say what is the concentration of the biomolecules, or what is the concentration of hydrogen peroxide present, and therefore indirectly what is the what is the concentration of glucose present in the solution. So let me conclude this first lecture on the amperometric sensors by summarizing a few things. As I said, the amperometric sensors essentially responds linearly to the reactants to be measured. Remember that for potentiometric sensors, it became a log because of the screening. Fortunately here, if you increase the concentration by a factor of 100, you do get a factor of 100 increase in the current. That's pretty good compared to what happened in the potentiometric sensors. And another thing is this KF and KR, the reaction rates, well, that depends on the voltage you apply to the electrode itself. You want to, the higher the voltage you apply, better it is, because then you'll have more current. The two levels will become more and more aligned. However, if you apply too high a voltage, then yes, this current would be large, but there may be parasitic reactions which are other levels sitting close by, which will essentially contaminate your signal. These parasitic channels you don't want to activate because that will reduce your selectivity. Now, I mentioned the 3 electrode configuration is very important in order to get specific ref voltages for each one of the electrodes. Because otherwise what will happen, the partitioning between the voltages between the working electrode and the reference electrode may not be well defined. And if it is not well defined, then it will not be a very robust sensor or predictable sensor. But in many cases, putting 3 electrodes are difficult. And so in that case, working with 2 electrodes requires extensive calibration before you should take the results for granted. And the important thing is, yesterday I just told you about glucose sensors. Well, no problem. If you wanted to do nitric oxide sensor, remember the NO. Remember the 3 types of molecule we talked about, small molecules. Then we talked about DNA and protein, virus and bacteria, the 3 classes. Many small molecules you could use by amperometric method to actually sense it, because it's very selective and essentially the chemistry is well defined and the response is linear, not logarithmic, and so therefore it is really used in wide variety of sensing applications, especially for small molecules. So I'll stop here. In the next class, we will talk about, on the next lecture, we'll talk about the second part of the amperometric sensors. Today we just focus on the sensor itself. The enzyme, how it reacts with the glucose and all those things. We really didn't think about much. In the second lecture, we'll talk about that. And until that time, take care.